Good morning. So it turns out I was on sabbatical for a few months in Switzerland, and I had the opportunity to teach a class, but I found the students, the graduate students, extremely shy. I guess it's because there is no homework, there is nothing. They just have to take a final exam at the very end, for which I won't be there because I came back already. Anyhow, so I was trying to encourage them to ask questions. So I started the chocolate scheme, which is you will get a chocolate for every question you ask, no matter how simple or trivial it is. Unfortunately, I don't have Swiss chocolate, but I have Cadbury, British chocolate. And I have very good aim. So at any time you ask a question, you'll get a chocolate. Okay, so let me just give an overall discussion of what we are looking at, why the system is interesting. So imagine you have electrons in a box. This could be 3D or 2D, but we normally work in a 2D system. So as you know, these are fermions. So even if you cool them to very low temperatures, you would still have to fill up the energy levels up to the Fermi level. So at t equal to 0, you still have kinetic energy. And that kinetic energy is of the order of the Fermi energy. So that wants to kind of randomize the electrons, if you wish. The Fermi energy, you could write it as density to the electrons, say, so have a constant density of states. So it's proportional to the density, and the density is proportional to 1 over r squared, where r is the average electron-to-electron spacing. Now, a competing energy, which we are interested in, is the Coulomb energy, and this one goes as E squared over R. So you have different dependencies for these, and you can see from the simple relations that if you write the ratio, Coulomb energy to kinetic energy, this goes as R, which means if you make the system more dilute, you have it more interacting. So it's a little counterintuitive. You would think if you pack more electrons, they are more interacting. But the problem is the kinetic energy or the Fermi energy goes up more if you put many. So in our world, the samples that we study, as well as many other people, other groups, we aim to make dilute electron systems. But now there is a problem, and that is disorder. Because if you make a system very dilute, especially any potential disorder, defects, impurities could disrupt the system. They typically have a very low Fermi energy, and this could cause a problem. So a way to overcome this is by making modulation-doped semiconductors or selectively doped structures. So you take a layer of layers of gallium arsenide, for instance, here, and you sandwich that layer by aluminum gallium arsenide. So this is the conduction band edge, and this energy is higher here than here. Then what happens is if you put dopants here, say in this case silicon, then the electrons can go to the quantum well. So you form a system like this, where the electrons are here in the quantum well, separated from the ionized impurities by a distance which you can control. So this distance we can control. We can make it 1,000 angstrom or micron, and that of course changes the density here. But overall, it's controllable. So essentially, we are separating the electrons from their parents, from the ionized impurities. The result of it is that in this plane, you get very good quality or long mean free path of the order of 0.1 millimeters. So at low temperatures, if you have quenched the phonons, then the mean free path is quite high. Another way to look at it is the mobility of the electrons, how they respond to an electric field, how fast they go, and it turns out that is very high, 40 million. It's the highest in any semiconductor. So this is the system that we look at. You could also make it a double layer, bilayer, by making a double quantum well system and then putting the impurities here. So you could make this barrier narrow enough so that the electrons are interacting in the two layers. In the talk, I'll tell you a little bit about these. So you notice my talk is a combination of materials and physics, because for this system, it's what we spend much of our time making these samples. So here is an example of a structure. It looks very complicated, but the main action is here. This is the gallium arsenide quantum well where the electrons are. These are the barriers, and these are the doping layers, the silicon doping layers. But you notice there is more than this simple structure. There's a superlattice here and so on. So all of this are designed or used so that this 2D electron system is as good quality as we can get it. The way this is done is in a molecular beam epitaxy. So imagine a very high vacuum chamber. The vacuum is essentially 10 to the minus 12 torr, the base pressure. And in this vacuum chamber, you have different ovens, aluminum, arsenic, gallium, and so on. And then the wafer sits here in front of these ovens, and by opening and closing little doors, little shutters, we can send in different species. So that's how you grow this, essentially layer by layer, atomically precise layers we could put down. You could, of course, control the material composition. You could, for example, open gallium and aluminum at the same time, and then you would be growing gallium, aluminum, arsenic. The open atoms, everything is controlled. So you could call it wave function engineering. Essentially, you could make this layer and its wave function any way you wish. So the important thing is this, for the high quality, is the base pressure, 10 to the minus 12 torr. So in fact, since nobody has asked a question, then I'll ask you a question. How many atmospheres is 10 to the minus 12 torr? So one atmosphere, how many millimeters of mercury is it?
60.
Yeah, you have to raise your hand so I know who to give the chocolates to. I have a finite number. So who said 760? Raise your hand. Okay, fine. You both get chocolate. So based on that, then what is 10 to the minus 12 torr?
10 minus 14 atmospheres. 10 minus 14 atmospheres.
10 to the minus
14.
15. Are you looking it up?
That's in my head.
You get the empty box. Wow. Yeah, so 760 millimeters, right? So this is roughly 1,000 millimeters. So this is 1,000 times better. So it's 10 to the minus 15 atmosphere. So that's quite good. So those guys in the back.
Thank you.
Oh! Sunu made me sign a form for injuries, so don't worry. We are covered. Okay, yeah, so it's extremely good. The other one I'll give you at the end. So the net result is the residual impurities are extremely few. So as you're growing these layers, the residual impurities that you don't want to get incorporated are very few, about 10 to the 13 per cubic centimeter. You remember Avogadro's number is 10 to the 23. So this is 1 part per 10 billion impurities that you get incorporated. These are important because you could put the intentional impurities wherever you want, but these unintentional impurities could get incorporated anywhere. So that's why you need a very good vacuum as well as very good source material to to do this. Anyhow, so all the samples that we'll talk about, all the physics is done in these types of samples. And now we come to the first physics part of it, if you wish. So these are placed in a high magnetic field, perpendicular field, and that leads to Landau levels. So the constant density of states now becomes a series of spikes separated by the cyclotron energy. And the key parameter in all these experiments is the filling factor, which is how many Landau levels we are occupying at a given magnetic field. And that is easily calculated. The degeneracy of each of these Landau levels is EB over H. It grows with magnetic field. And the filling factor is density divided by that degeneracy. So you could have different Landau levels. So at some magnetic field, if your Fermi level is here, you have just 2 levels, or 3 if your Fermi level is here, and so on. Or you could go down here to have fractional filling. So the amazing thing is, in a system like this, just a simple 2D system, and sweeping just one parameter, which is magnetic field, you get so many states. These are, for past 30, 40 years, discovered in these 2D systems. Most of these were discovered in gallium arsenide, except for this first one. Of course, this was the integer quantum Hall effect, which was discovered in silicon MOSFETs. So these happen at different fillings. Like this is when you have only one Landau level occupied, or an integer number. This is a fractional quantum Hall effect, where you have a fractional filling, say 1/3. Near 1/5, what happens is the electrons tend to go into an ordered array. This is the so-called Wigner crystal. So we talk about these during the talk. A particular place is 1/2. When you have this last Landau level exactly half filled, you get these composite fermions, flux, 2 flux plus an electron, quasi-particles. And then there are, of course, skyrmions and stripe phases and so on. So you have so many phases. That's what has fascinated me for many years, that it's a very rich system that we have. So these you could probe them by many experiments, but the simplest is transport. That's what we talk about today. So you just measure the resistance of the sample as a function of the perpendicular field. And this lowest trace is the resistance. This curve here is the Hall resistance. And what you notice is the Hall resistance, instead of being a straight line, which would be predicted classically, it has all these steps. So these are the quantum Hall states. For example, here, this is the nu equal to 1. And you have, of course, other ones, 1/3 and 1/5 and so on. And you notice right here, when you go to very high fields or very low fillings, when the last Landau level is less than 1/3 full, what you see is new states or new phenomena. The resistance, for example, becomes very high. This is 200 times bigger than this resistance here. This is factor of 100 reduced. And it behaves as an insulator. So this is the, for example, the Wigner crystal. So you can see just from these traces, you can learn quite a bit. So again, let's go over a couple of these carefully, because during the talk we'll need this. So the first one is the integer quantum Hall effect. So what happens here, if you have any disorder, the bulk of the 2D system, when an exact integer multiple of Landau levels is occupied, it becomes insulating, and all the conduction happens near the edge, the so-called edge states. So you get essentially 0 of resistance. So if you look at the rho XX trace here, for example, resistance is practically 0. Not exactly 0, but very close. And that is when you have the Fermi level, say here, only one Landau level occupied. Whenever the energy, Fermi energy, is in a gap between Landau levels, you get the integer quantum Hall states. It is harder to explain why the Hall resistance becomes quantized, but overall it's a single body phenomena. You can explain it based on that. So that's the integer quantum Hall effect. I put this on purpose because sometimes people forget this is the ancestor of all topological insulators. It's the 40-some-year-old ancestor of these states, because this is not insulating and the edge is conducting. So now if you look in these traces, you see similar phenomena elsewhere. For example, here you have a plateau. Resistance goes to 0. But this happens when the last Landau level is only 1/3 occupied. So your Fermi level is no longer in a gap of a single particle density of states. So the question is why? And the answer was given first by Laughlin, who wrote a wave function to describe this. So this is pairs of particles, product of pairs of coordinates of pairs of particles to the third power, for example, for the 1/3. So this wave function keeps the electrons away from each other. No two of them come close. But of course, there is no long-range order, no Wigner crystal in this case. But short-range correlations are strong. So this is a description for the 1/3 state. 1/5 would be, this would be power of 5. Now, let me give you an explanation for this based on this composite fermions again, because we need this for the rest of the talk. So suppose you're at 1/3, so your Fermi level is deep in the last Landau level. So in the single particle density of states, there is no gap, but you see phenomena like this, that there is a fractional quantum Hall state. So one way to explain it is this. I just put these arrows to bring to your attention that if you look, for example, from here, 0 of magnetic field, you see this all trace here, there's the plateau. If I shift the 0 of magnetic field to here, you notice this looks very much like this, qualitatively at least. There's a plateau and so on. Or if I shift it to this point, again, this is a plateau, and then here's another one. So it replicates as you go to these particular places. And these particular magnetic fields correspond to even denominator fillings. For example, 1/2 exactly here. So this is when your Fermi level is exactly halfway. The last Landau level is exactly half full. This one is exactly quarter full. So this phenomenology prompted Jainendra Jain and others to come up with a picture for fractional quantum Hall effect in terms of composite fermions. So the picture is the following. You attach two fluxes to an electron using very good glue that only theorists know how to do this. As an experimentalist, I have never done this. But, so you attach the fluxes to the electron, and then you form this composite fermion. So essentially, you have a system like this where there are, say, 4 electrons and 8 flux quanta. This means exactly filling factor 1/2, twice as many flux quanta per electron. And then once you attach them, then you get these quasi-particles. And these no longer have any magnetic field left. So they behave as if there is no external field. They also don't interact, or interact very weakly. So it's an amazing, if you wish, transformation that transforms a bunch of interacting fermions to these quasi-particles which behave as if the 14, 15 Tesla magnetic field that was there is gone. So in principle, these should have a density of states just like the electrons do at zero field. So it's a two-dimensional density of states. They should have a Fermi energy, behave again as if they're at the zero field, exactly at 1/2. Now, if you go away from 1/2, then you have some extra field. So the effective field would be non-zero, but exactly at 1/2, you would have the effective field for these zero. Yes, sorry. Yeah.
Why 2 flux quanta instead of 1?
So you could actually attach any. I mean, you could attach 3, then you get bosons. So it depends on how many you attach. The even number leads to a composite fermion, as shown here. In a second, I'll tell you what happens when you add one more flux. Just wait for a second and then. Yes.
After you attach the flux quanta, will the electron become bigger or?
You mean the quasi-particle would be bigger, right?
The size of the composing fermion.
Experimentally, I don't know any direct measurement. Later, I'll show you some data for 5.5, near 5.5. These may be, but overall, no. There is no experimental evidence. And the theorists, I think near 1/2 at least, no. It should be still of the order of magnetic length, right? Okay, so any other questions? So, all right, so now let's see how this can explain the fractional quantum Hall effect. Right, so exactly at 1/2, we have one electron plus two flux quanta, so we have one composite fermion's effective field is 0. So that's right here. And there is no quantum Hall, of course. This is like 0 magnetic field. Now, if you sweep the field away from this position, now the effective field is non-zero. And exactly when you come to 1/3, now you have 3 flux quanta per electrons. So you have the composite fermion plus an extra flux. So this is like nu equal to 1 of the composite fermions. And that is why then you would say there should be a quantum Hall. And so on. There are many other states here. There's 3/5, 4/7. These other states, you could explain it all based on this simple picture. So you asked the question, so you could theoretically attach 3 fluxes to an electron. It turns out that forms a boson, which condenses into a fractional quantum Hall state. So that would be another description, right? But all this stuff I'll talk about is near half filling, and so we are focusing on the composite fermions. Okay, so the main message here is that if I look around 1/2 or 1/4, the electrons should behave, or these composite fermions should ignore the big magnetic field. Let me tell you about one more state, because we'll come back to this again later, and then I'll show you the latest data. This is all a review, if you wish. So near 1/5, when the last Landau level is very low, has very low filling, then a new state comes. Again, this was predicted for many years by theorists, and in fact, Dan Sui and Stormer, who discovered the fractional quantum Hall effect, they were looking exactly for this, the Wigner crystal. This was predicted, but of course they saw something even much more exciting, something that had never been predicted. So anyhow, so this is an ordered array of electrons. The electrons try to minimize their Coulomb repulsion, so they form a triangular lattice. Now you could ask, why is it insulating? And the reason is it's very likely pinned by some disorder that we cannot get rid of in realistic samples. In other words, if this were completely free to move, you could slide it without any effort. But if there is any disorder, it could pin it, and then it shows as an insulating phase. So there is plenty of indirect evidence, nonlinear IV, microwave resonances, NMR, but there is, I would say, still no direct evidence like, say, X-rays or, measuring the phonon dispersion directly. Okay, so that was all introduction. So the rest of the talk, I'll show you data for 4 different 2D systems of this sort. One is the gallium arsenide holes. Next one is gallium arsenide electrons. Then aluminum arsenide electrons. So this is when we put the electrons in aluminum arsenide rather than gallium arsenide. And then at the end, a few words on a bilayer system. So these are all based on gallium arsenide, aluminum arsenide. This particular statement is aimed not at you, but at the funding agencies. Because they always say, gallium arsenide, dead. And I say, no, here. Here is so many new things that you can see. So I hope you appreciate that. This is all in this. Okay, so these are the topics in these systems. One of them is the transference of Fermi contour anisotropy to composite fermions. Composite fermion waltz to the tune of a Wigner crystal. near 5½ and then at the end the aluminum arsenide electrons which are anisotropic. So these don't make much sense to you yet, but we go on, you can see it. So the first question for the talk is this. Suppose you have a system of electrons, say in like gallium arsenide. So at zero magnetic field, the dispersion is isotropic, it's very simple. You have the conduction band, so electrons have a Fermi sea or a Fermi contour, which is circular. Now you go to near 1/2, so you have now composite fermions, and based on what I told you, you'd expect that they also have a Fermi sea with a well-defined Fermi contour. And there is no reason this shouldn't be circular, so it's circular. You noticed I drew the area of this bigger than this. Can somebody tell me why for a chocolate? I'll give you a hint. Factor of 2 bigger.
Zeeman splitting?
Very good, yeah. So can you say what happens?
Zeeman splitting.
Yes.
So the flat Landau bands just get split. That's why essentially if you have like a half filled initial band which includes spin, that means that you will have 2 Landau bands that are, the first one is completely filled.
Right. Essentially at zero field, you have the 2 spins, right? So the degenerate, this is very low field. So in your Fermi C, you have both spins. But when you go to very high field, like 15 Tesla, then in the system at least, the system becomes fully polarized. So composite fermions are fully polarized. And that means that the Fermi C they need is twice as big. Kf is square root of 2 bigger. So all these answers come from way back. Wow. All right. Yeah, good. So the question here is, what if you have a Fermi C which is not isotropic? So you have something like this, say elliptical, has a form like this. What happens to the Fermi C of composite fermions? Do they inherit some anisotropy, or do they stay have the same form, or do they become circular? So it's a question. As an experimentalist, we asked theorists, first time maybe 10 years ago, and they usually would say not obvious, because it turns out the physics of the composite fermions is dominated by interaction. The main length scale that comes in is the magnetic length, which doesn't have direction, and so they would say, oh, maybe it should be isotropic. So anyway, so that's why it was interesting to check it. So the next question is, experimentally, how can we probe the shape of the Fermi C? So one way to do it in transport measurements is the following. So in reciprocal space, you have a Fermi C, say, that is circular. So this is Kf, Fermi wave vector. And now suppose you put a small magnetic field perpendicular, so the electrons go in cyclotron orbit, and they have an orbit like this. So this is in real space. This is the cyclotron radius. So as you know, this orbit essentially has the same shape of this, but rotated by 90 degrees. So if you can measure the shape of this, you could infer the shape of the Fermi C. And this is a simple relation between the cyclotron radius and the Kf. So that's the plan, to measure the cyclotron radius of the composite fermions. So again, one way to do it is you could put a modulation, essentially. You could modulate the density of the 2D electrons in one direction. So this is the modulation. All you need is a very small amount, less than 1%. And it turns out, so the period, say, is A. It turns out whenever the cyclotron orbit fits in a period, or 2 times the period, or 3 times the period, you see a minimum in the resistance. These are well known. They're called commensurability oscillations, or Weiss oscillations, named after Dieter Weiss, who first reported this. or geometric resonance, because essentially you see a resonance of the orbit with the period. So using this technique, we could measure it, for, of course, for zero field particles, electrons, and we could measure it also for the composite fermions. And by putting the, so if this thing is elliptical, then you expect this to be elliptical, rotated by 90 degrees. And by putting these stripes in the different directions, we can probe it. So this density modulation, the way we do it in our lab, you want to apply as gentle modulation as possible. So we don't put gates or etch or anything. We just put stripes of photoresist, or electron beam resist rather. So this is a micrograph from the top. This is the side view. So these are the E-beam resist stripes that are put on the surface. So it turns out these have a different thermal contraction coefficient compared to gallium arsenide. So when you cool it down to low temperature, they induce a small strain near the surface, a periodic strain. Gallium arsenide is piezoelectric, so that strain, when it propagates to the electron system down here, produces a small electric field that modulates the density. So it's a very benign way, a very harmless way of modulating the density by putting these stripes. So here is some experimental data. So this is for holes. This is the system where we measure the anisotropy, or at least the data that I'm going to show you. So for 2D holes in the valence band, but the physics is similar for this purpose. So here again you can see cyclotron orbits fitting the period. This is the top view, and here's the data. So if you look at the unpatterned region of the sample, you notice the resistance has not many, that doesn't have any features, and then it starts to oscillate. This is Shubnikov de Haas, so that's normal behavior, what you expect for a 2D system. This eventually shows quantum Hall, of course, and fractional quantum Hall. It's very low field. But if you include the period or the pattern on the surface, then it shows these clear minima, 4, 3, 2. So these are the minima correspond exactly to these orbits fitting, the cyclotron orbit fitting in the integer number. There is a phase here, so the precise expression is this, but overall you can see qualitatively at least, you can get the KF from these positions. So now let's look at high field for these samples. So this is a trace extended now to 15 Tesla. So the unpatterned, or the reference part of the sample, doesn't show much near 1/2. It shows a broad minimum. This is what all samples show typically. And then these are fractional quantum Hall states that come 2/3, 3/5, and so on. But near 1/2, there is not much. The pattern sample, that has very clear features. It has a deep minimum here. That's similar again to the low field data. If you look here, also, you notice the pattern one has this deep minimum. There is some physics behind it. And then it shows these minima. So these correspond to essentially these commensurability minima. So just like the electron case, or the zero field particles, where we could get the KF and compare it to the experiment, we could do it here also. I forgot to mention, these arrows or tick marks are at the expected positions based on a simple expression that we know. So we are going to look then carefully at these features, and the effective field measured from here to the positions of the minima gives us the shape of the Fermi contour. Now, for this experiment that I'm showing you, we are using 2D holes rather than electrons in gallium arsenide, and the reason is their dispersion is very sensitive to strain, becomes anisotropic, and that is what we are interested in probing. So at the zero strain, the holes have a little bit of unusual Fermi contour. It's not a circular contour, but you notice it's warped. It's also spin split because of spin-orbit interaction. But in the experiment, we really can't resolve the small or spin orbit interaction split bands. So this is where there is no strain on the sample. I'm not talking about the strain from the stripes. This is global strain that we can put on the sample. So the Fermi contour clearly has a fourfold symmetry. But if we apply strain, 2 10 to the minus 4, so this is a small strain, but it's enough to make the Fermi contour extremely anisotropic. These are calculated Fermi contours for holes. So with strain, we can make them anisotropic, or this is negative strain, become anisotropic in the other direction. We're just stretching the sample. The way this is done is to glue the sample on top of a piezoelectric actuator. So this is about a centimeter on the side approximately. So for this one, as experimentalists, we do it ourselves. We use really good two-part epoxy, so our flux quanta are the two parts, the epoxy, and that glues them very well to the piezo, holds at low temperature. And then by applying voltage to the piezo, we can strain the sample one way or the other. And the sample has a L-shaped hall bar also on the surface with those stripes. And you can see from this picture, if the Fermi contour has been elongated in this shape, for example, the cyclotron orbit has a similar shape, but perpendicular. So that's why it's elongated in this direction. And the way this now shows geometric resonance with the stripes is different from in this hall bar, right? Because here it's the short axis of the cyclotron orbit that can resonate here. So essentially, this would say for the two directions, we should see different condition or different field for the resonance. And indeed, that is what we see. So here are 3 traces shown for these 2D hole samples. The black one is no pattern. So you notice again a smooth minimum near 1/2. These 2 traces are strained. They're pattern and on this piezo strain. One of them is strained positive, one is negative. And what you notice is that there is a difference in the minima positions. The 1/2 is here. The blue are shifted away compared to the red. So this clearly says for the 2, I'm sorry, it's a different strain. These are the same strain, just the 2 arms of the hall bar. The red is one arm, blue is the other arm. So if the Fermi contour is distorted, then it shows up here clearly as these. So right away the answer is the composite fermions do have anisotropic Fermi C. So how does it relate to the Fermi contour of the fermions, the zero field particles? And here is the comparison. So for the holes, the zero field particles, this was the calculated contour that I showed you, and the experimental data are shown here, the blue and the red. So they agree reasonably well with the calculations, and as I said, we can't get the splitting, at least in these samples. So the same measurements from the high field for composite fermions show this kind of Fermi contour. So we can only measure it in the 2 perpendicular directions. But you notice that this is also elongated doesn't look elongated. Oh yeah, okay, good, on my angle. Right, so this is elongated in the same direction. You notice the area is bigger than this. That's because of the spin polarization. So it all agrees, but clearly this is distorted, just like this. The question is by how much? Can we quantitatively link these? And the answer is yes. So one way to parameterize it is to look at the anisotropy ratio, if you wish, which is the long axis over short axis, the Fermi wavelength along the 2 directions. Let's call this alpha. So in this figure, we are plotting now the alpha for composite fermions measured from the data that I just showed you as a function of strain. So these are the data points. So the Fermi contour essentially goes from a shape like this to a shape like this. And of course, right at zero, it's circular, but it definitely gets distorted when you're off from when you apply strain. So this is the anisotropy of composite fermions. If I add the data for the fermions, for the holes near zero field, that's this brown or orange line shown here. So you notice there is a very good agreement with the data, with the composite fermions, except that what I've done is plot the square root of the anisotropy for holes, for the fermions. In other words, the square root or the anisotropy of composite fermions goes as the square root of the anisotropy of fermions. So this is I would say, a simple experimental finding. There is no adjustable parameter here. The only thing I've done is just plot the square root, and that's how it falls on top of it. So you can say, so is that reasonable? Is it reasonable that they get transferred, but with a square root behavior? And the answer is theoretically, at least in numerical calculations, yes. So these are calculations done by Matteo. Oh, yeah, here it is. Ippoliti, he's actually in the audience, in Professor Robin Bott's group. So they were doing these calculations same time as we were doing the measurements. So you can ask him for all the details, but at the end of the day, if you assume Coulomb interaction, then they get, in fact, exactly the square root behavior. This is the calculated anisotropy of composite fermions plotted versus anisotropy of fermions. This line has a square root of 2, a square root dependence. In the calculations, they find that this depends on the interaction. So for Coulomb interaction is this. For dipole interaction, they see a different power law. So Robin and Matteo keep coming to us and say, can you change your interaction? So not so easy to do, but maybe at some point. So anyhow, but at least for the Coulomb is clear. There was a later paper, this came late last year, Liu and the company, Das Sarma is one of the co-authors. So they look at the square root of square root behavior, and they say this is actually a universal rule. In their theory paper, they claim that this is a universal rule for Dirac fermions with long-range interactions. So they consider it actually as a test that if it is showing square root, this means that the composite fermions are Dirac particles, Dirac fermions. I'm not going to go into details, but this has been a big question past 4 years, 5 years about the origin of composite fermions. I could show you, but let me save this for the discussion later, a simple way of telling you where the square root comes from, a way that experimentalists can follow. But I'm going to go to this one here. But before we go there, let me stop, see if you have questions. Yes?
Can you comment a little bit about this Dirac fermion proposal? So should the Fermi level be at half filling exactly at the Dirac point? Where is the Dirac point expected to be? And how does it relate to your experiments?
It doesn't. I mean, to the best I can tell. The experiment just says the square root. But what I was saying is the theorists that in that paper, they say that the square root would be is consistent with the Dirac fermion origin for the composite fermions. In other words, if they weren't Dirac fermions, then they wouldn't show square root. Maybe Matteo can comment. That is what they say essentially, right?
Yeah, they consider Dirac fermions with Coulomb interactions in various models and find that the anisotropy of the Fermi contour gets normalized by interaction to the square root of the non-interacting one.
But only for Dirac fermions.
Yeah, so they don't consider Landau levels or anything, just Dirac fermions in any band model.
Right.
So then, but if you have composite fermions, they're weakly interacting, so you don't necessarily expect that to apply. But I guess if you were getting them out of a Dirac band, then there would not be that.
Right.
Follow from that.
So I'll save you one for after lunch, because I don't want to waste your appetite. But Matteo, you get one. Oh, sorry. Okay. So I can maybe continue. We could pause for a minute if you'd like, but maybe we should continue so you could get to lunch. So the second part is this bilayer system. And let me just remind you again the two states that are involved here. So one state of 2D electrons that presumably happens at very low fillings is this near 1/5 is this Wigner crystal. So imagine you have such a state, and then you remember near 1/2 we have these composite fermions, where again there is plenty of evidence, such as the ones I was just showing you. The idea in this measurement was whether we could probe the Wigner crystal using composite fermions. So the idea is shown here. Imagine a sample which has two layers, and one of the layers has very low density, so it's in a Wigner crystal regime. So the filling factor is very low, say 1/10. So it has a Wigner crystal like this. These are charges of electrons shown in this plane. The other layer, which is very nearby, so it can feel the potential of this Wigner crystal. We put it at a different filling. We have gates on these samples, so we could change the density. So the density of this is so that it's near 1/2. So we have composite fermions. So then, if composite fermions, I showed you, whenever they see something periodic, they like to show some resonance effects. It turns out in this case they could go around 1 or 3 or 7 of these potentials, and we are assuming that the position of these gets reflected as a small modulation of the electrostatic potential here in this plane. So the goal then was to see if we can see commensurability of composite fermions dictated by the Wigner crystal. So just to tell you, near zero field, of course, these are experiments were done many years ago, not Wigner crystal, but essentially if you have a periodic so-called antidot. So this is a system of 2D electrons, and on the surface, essentially it's punched holes. So in this experiment, they're just punching holes into this 2D system, so there are no electrons where these little dots are. So if you have a system like this, as you sweep the magnetic field, when the cyclotron orbit of electrons goes around one of these antidots, or 3 or 7, you notice it shows very clear maximum. In this case, it's maximum. So you have a big peak here, and this is because of this commensurability. Our idea was, instead of this, of course, doing it lithographically, is by putting the Wigner crystal layer nearby to produce a potential like this. This is just to show you that composite fermions also do this. Again, the Wigner crystal layer is not there. This is with the antidot system. This is Wu Kang's data back in '93. What he showed is that right near 1/2, there are indeed, maybe you could see it here best, right near 1/2 there are these maxima. They correspond to a cyclotron orbit of composite fermions going around an artificially antidot superlattice, artificially induced superlattice. Okay, so now how does it work for the bilayer Wigner crystal composite fermion system? So we have a sample like this. This is the low density sample. This is the high density. We get to these densities by changing the spacer layer thicknesses. And also with the back and front gate, we can tune the densities. So essentially, this layer is put in Wigner crystal state. The other layer is right near 1/2. And this is a summary of the data. You can look more details here. Suppose I get rid of this layer by gating it out, meaning the bottom layer, there are no carriers at all. So then you have the top layer, which is just near, it's a composite fermion system, 2D system. So it shows the fractional quantum Hall states and a smooth minimum, just like other samples do. So there is not much feature, not many features near 1/2. But if we put electrons in this layer, very few of them, then you notice here, you can barely see it, but there are some features in the resistance that come about. And now we look at these very carefully. So this is not the temperature dependence. This is this region shown blown up so that you could see the details. So this is the base temperature. So you notice near 1/2, this is 1/2. There is a maximum here, and maybe a glimpse of it here, but on this side you can see it. So these arrows are not to show where the maxima are. These arrows are the expected positions of these maxima based on the density of composite fermions and based on the density of the Wigner crystal electrons that we have. So that's important. So there is a very good agreement between where you expect to see features and where we see them. So 137 come from these orbits that I'm showing you here. And then this axis here is, or the traces as a function of temperature, 95, 115. So by the time we go to like 400 milli-K, these features are gone. But in this range, you can see them even up to 142. There are some. They're not perfect. Sometimes they're missing, but sometimes they're very clear. These two red and black, by the way, are sweeping magnetic field up and down. So sometimes there is hysteresis that we don't understand. But I would say the main conclusion here is that there are features, and they agree reasonably well with what you would expect for electrons or composite fermions in this layer going around the potential produced by the Wigner crystal. And of course, you can get the lattice constant and the periodicity, which turns out to be consistent with the triangular lattice. So this was probing the Wigner crystal with composite fermions. That's why I call this composite fermions, waltz to the tune of a Wigner crystal. This was, by the way, the original title of our paper. But Physrev Letters is so dry, they said, this is not very scientific. I'm sure Science and Nature would have loved this. So they made it the most boring title you can imagine. But anyhow, so composite fermions dance to the tune of Wigner crystal. And then this shows you that the Wigner crystal returns the favor. So the Wigner crystal essentially dances to the tune of the composite fermions. The way you can probe that is through an experiment done in collaboration with Lloyd Engel. So this just came out a couple of months ago. So what Lloyd and Anthony Hatke, his postdoc, did is to look at microwave resonances. So this is essentially conductivity measured as a function of frequency. And often in the Wigner crystal regime, you see these very clear resonances. You can see it here at this around 2 gigahertz frequency. So these resonances are attributed to the pinning mode of the Wigner crystal. So you have a domain of the electrons forming Wigner crystal, and it's slushing back and forth collectively, and that leads to this. So there's a long literature of understanding these resonances. What is interesting here is that if you measure the resonance as a function of the density of the composite fermions, you see that clearly this moves around. You can see it very well, and this is a summary of this. The peak position of the resonance depends on the filling factor of the composite fermions. Whenever the composite fermions are in a fractional quantum Hall state, 2/3, 3/5, and so on, that frequency is low. The resonance frequency goes to lower values, otherwise they go to high. So this says that the Wigner crystal is resonating or the frequency depends on what is happening here. Whenever this goes into an incompressible state, meaning these fractions, the frequency drops, and there is an overall behavior. So in this paper, all of this is analyzed, and the main conclusion is that indeed you are affecting the resonance frequency. Yeah, yes?
Is this a statement depending on the density of the impurities and stuff? Because you said impurity pin the Wigner crystal.
The pinning frequency often depends on the disorder, but presumably we are not changing much, right? In this experiment, all we are doing is just keeping everything fixed, sweeping field, and then these other ones are for different densities of the Wigner crystal. But overall, it's right.
But would you expect this resonant frequency to depend on the density of the impurity, for example?
Yes, I mean, in an indirect way.
Yeah.
Depends on disorder. It depends on the domain size and, so yes, then there's a long literature trying to understand it. Yeah, right. Chocolate for you. It's the easy one. All right. Good. So then I'll go to the next topic, which is composite fermion fermicy near 5/2. So if you look in these traces, resistance traces, you notice in this range from here on, there are many fractions, 6/11, 5/9, here, there are fractions here, near 3/2, there are lots of fractions, and they're all at odd denominators, like 3/5, 4/7, and so on. That goes way back to the Laughlin wave function. These are fermions, so you need antisymmetric wave function, so they have this odd. So there is no fractional quantum Hall state at 1/2 or 3/2, just a smooth minimum. This is where the composite fermions are. That's what we were studying. If you go to the second Landau level, so this is the lowest Landau level, the two spins. That's why filling is 3/2 here, or between 2 and below 2. So this is the lowest Landau level. This is now the first excited Landau level, n equal to 1. And you notice there are fractions here, and in particular, there are very interesting ones, like the 5/2, even denominator, or 7/2. So this is very interesting region. And then if you go beyond it to n equal to 1, 2, 3, higher Landau levels, then fractions are pretty much gone. The stripe phases come, and that's interesting by itself. So the interesting thing is here for this purpose. So this comes because of the node in the wave function. In the lowest Landau level, you have say wave function like this. This is in the plane. For the second Landau level, you have, or the excited one, you have a node, and then here you have two nodes and so on. So this turns out to change the interaction, very subtle, and that brings out changes the fractional states here. But at the end of the day, you do get a 5/2. So it's even denominator, and the question is, what is its origin? One popular theory says that this is pairing of composite fermions here, 1/2, and of course, you may have heard already, this could be non-abelian and good for topological quantum computing. So our goal was to look around 5/2 and see, is there any sign of composite fermions there? So this is using the same technique as before. So here is 5/2. You notice a deep minimum, and a plateau. So this is the fractional quantum Hall state at 5/2, the gallium arsenide electrons. And you notice on the sides there are these two clear minima, whose positions match very well with what we expect for the composite fermions to go around the period. So the answer is yes, there are composite fermions. And maybe more importantly, they are fully spin polarized. In other words, these arrows are placed at the expected positions if the composite fermions were fully spin polarized. If they weren't, then it would be a factor of a square root of 2 smaller. So it would be very clear that they are not. So these were the main conclusions, and these are consistent with the this picture, that it's composite fermions are there, and if they're fully polarized, it's consistent with the non-abelian nature. Okay, good. I'm going to go to the last topic of the talk. And this is anisotropic even denominator fractional quantum Hall states in aluminum arsenide quantum wells. So I told you at the very beginning, I'll show you data for different systems. So remember, this was 2D holes. This was 2D electrons, bilayer. Sorry, this was, I guess I reversed the order here. This is 2D electrons, near 5.5, single layer. This was the bilayer gallium arsenide electrons. And now this is a new system where we replace the gallium arsenide layer with aluminum arsenide, pure aluminum arsenide. So, so this is what we are doing. Instead of gallium arsenide, we just grow, say, 200 angstrom of aluminum arsenide. Now, two things you need to know. First, the band structure of aluminum arsenide is very different from gallium arsenide. It's similar to silicon, and that's why I'm showing you silicon here. So the top of the valence band is here at the gamma point, but the minimum of the conduction band, instead of being at the gamma point, is somewhere here. It's on the way from gamma to X at the so-called delta point. So if you get electrons here, if you accumulate electrons in, say, a silicon MOSFET or in silicon, where they would be are in these ellipsoids in bulk silicon. Right, so you have 6 valleys shown here. The effective mass is anisotropic if you go along this axis versus perpendicular. So you have a multi-valley system in silicon. The minima here in silicon are inside the first Brion zone as shown here, so you have 6 full ellipsoids. So aluminum arsenide band structure is very similar to this, except that the minimum is right at the X point. So these ellipsoids are shifted out, so half of them hang over, half of the ellipsoid hangs over to the second Brion zone. Okay, so in the bulk you have a system like this. Otherwise, it's very similar to silicon. So in contrast to gallium arsenide, this has a very small mass, and a negative, reasonably small G factor and single valley. This is all at the gamma point, center of the zone. The aluminum arsenide has these 6 full valleys or 6 half valleys or 3 full valleys, and they are anisotropic. The masses are longitudinal is 1, transverse is 0.2, 5 times anisotropy. G factor is 2, and of course is multi-valley. So in fact, this is in this respect, this graphene is similar to this, and in fact, many of these valley experiments done in graphene now were done in this system already many years ago. So now, how do you get electrons trapped in aluminum arsenide? And it turns out, if you look at the gamma point as a function of space, so we have barriers, AlGas. This is aluminum arsenide quantum well. At the gamma point, the blue, as you can see here, there is no trapping of electrons. Right? The blue in the aluminum arsenide, the gamma point is in higher energy. But it turns out the energy at the X point of the Brion zone is indeed lower than the gamma or X of these barriers. So you could trap electrons in the aluminum arsenide. So this is something we first did many, many years ago. Then we made major improvements at that time, 2002. And then very recently, I'll show you some data, we have the breakthrough in making the quality even much, much better. This is Lauren Pfeiffer and Edwin Chong's work. So these are data from 2018, these latest samples. So these are electrons in aluminum arsenide. And you notice these traces look just like gallium arsenide. I mean, it's amazing how many fractions you can see. You can even see insulating phase near 1/5. This is 1/5 quantum Hall, and then the red curve, you know, this is divided by 40, so resistance is very high. So if I didn't actually tell you that this is aluminum arsenide, you couldn't tell. You know, this is almost as good quality. Mobilities are quite high, not as high as gallium arsenide, but given the large effective mass in the system, this is pretty good. And the trick, or the reason why this was improved so much is essentially very careful cleaning of the aluminum source. and also very clean MBE. And remember, I told you the vacuum, because aluminum is very nasty. It catches oxygen, any impurity that comes in the chamber. So it's very sensitive to that. So essentially, by doing this, we improved the quality of the aluminum arsenide, and that now meant we could change the quantum well width, do things that we do with gallium arsenide to optimize things, and this is the result of this. So now let me tell you a little more about the tunability of this system. So turns out the valley occupation depends on the quantum well width. Am I okay with time?
5 more minutes?
5 more minutes, yeah. So it depends on the well width. So in the bulk, I told you there are these 3 full ellipsoids or 6 half ellipsoid. If you grow aluminum arsenide and gallium arsenide, now you have confinement. So let's look at this one first. So if you confine the electrons in a quantum well, as you know, the energy level is something like this. Then what you get is that this valley becomes occupied. The reason is, you could ask a question, but you are rushed for a lunch. The effective mass here is bigger compared to this direction for these, so this has a lower energy. So this becomes occupied. And indeed, that is the case for very narrow wells. But it turns out for medium-sized wells, bigger than this, these in-plane valleys become occupied, and the reason for it is that aluminum arsenide grown on gallium arsenide is under slight biaxial compression. The lattice constants don't match. This has a slightly larger lattice constant, so it's under biaxial compression, and that pushes the energy of these valleys down. So for wide wells that I'm talking about, this is the case. Then we do another trick, if you wish, experimentally, and that is back to this piezo. In fact, this is the first time that we use the piezo was for this system. We glue them on the piezo. This is a quarter, and this is the finished product sample glued on the piezo, ready to go, in this case, to the magnet lab to go to 45 Tesla and very low temperatures. And this is a simple cartoon showing you that as we strain it, say as you squeeze in this direction, you transfer electrons from the X valley to the Y valley, or 1O valley to the O1O. So with enough strain, you could transfer all the electrons, if you wish. So it's a very nice system, because if you put them all now in this valley, now you have a anisotropic Fermi contour. In fact, that was our original goal, to do the experiments, the composite fermions in the system, and hopefully we'll get there, because now we have very good quality. Anyhow, so just to show you very simply how this manifests in experiments, it's very simple. We are measuring the resistance, Rxx and Ryy, along the 2 direction in the sample as a function of strain. So this is 0 strain, so both values are equally occupied, so we measure some resistance. But now suppose we are measuring Rxx and we are putting all the electrons in this X valley. The resistance goes up here because the effective mass is big in this direction. So simple Drude model will tell you this resistance should be higher. If you put the electrons all in the Y valley, and we are still measuring in this direction, now we are measuring along the transverse mass, which is the low mass, so the resistance is low. So in fact, this ratio ideally should be around 5. In the experiments, it's typically 3 or 4. But it's a very simple, if you wish, way to show that indeed you can transfer electrons from one valley to the other. You notice this is very small strains, 10 to the minus 4. So in fact, the resistance of the sample is extremely sensitive to strain. So you could use it as a piezo resistive strain gauge. I tried to sell this once to the Army as a proposal. The guys came and listened very carefully, and then they were very happy. This is really very sensitive. And then they asked me a question: would this fit in the soldier's backpack? Because that's what they're interested in. And I told them, sample and the piezo, yes. The cryostat. So I was honest, and we didn't get the grant. So So anyhow, so with this strain, you can change the valley population. With the magnetic field, you could change the spin population. So it's really a very nice system. In fact, this is the very first system where valleytronics, which many of you have heard of, was demonstrated. If you don't believe me, go read this. There is nothing before this that shows you that they could be manipulated. Anyhow, so the valleytronics, you can demonstrate what I just showed you. You know, the electronic properties depend on the valley population, manipulated by valley. That's exactly it. So there are many other experiments. So I'm just going to show you the last slide and stop. So in fact, there is a poster today by Shafayat Hussain, so you can see more details. So in this anisotropic system, we see something very unusual. So this is where all the electrons are put in this X valley. So the Fermi contour is indeed anisotropic. And that means the resistance along the X direction is higher than the resistance along Y. So Rxx is bigger than Ryy, as you can see here at zero field. But as you sweep field and you see quantum Hall and fractional quantum Hall state, all of a sudden, near here, it reverses. The red is much bigger than the black, and in fact, this red is divided by 2, so it's really high compared to the red. So it's extremely anisotropic. Those of you who are experts in this field, that reminds you right away of these nematic states or charge stripes. But it turns out this is even more interesting. Even though the resistance is extremely anisotropic, if you look carefully at the Hall resistance right here, it is quantized. You know this here. This is right at 3/2, even denominator. You have a very well quantized Hall resistance. So it is a very unusual state. It shows pneumatic-like transport, Rxx, but resistance is quantized. So that was the last one. This is the cast of players who make all of this possible. The ones in red, Edwin, Shafayat, Monk, and Kevin, are the current students in our group. The other ones are the ones who graduated and went to better places, Alibaba, Beijing University. And then for the MBE, we have Kirk Baldwin, Ken West, and Lauren Pfeiffer, who grow the best samples in the world. And some of the calculations I showed you for the band structure are from Roland Winkler, who we collaborate with. And then I'm going to just show you this as a summary of some of the stuff I told you, in case you want to ask questions. Thank you. 5 minutes good.
Yeah, just a couple questions.
Yes.
Do you have the energy gap data for the anisotropic 3/2 state?
No. So I invite you to come to the poster session. What happens is below some temperature, the resistances come down. So it is like a quantum Hall, as you would expect. But the range is very small. I mean, it doesn't change by much. So we can get an energy gap, right? I owe you a chocolate. Yes?
So for the piezo setup, when you apply the strain onto the sample, do you know like what's the top surface and the bottom surface? Is the strain the same or is there's a gradient?
So the one thing we do is we thin the samples. So typically they are 0.5 millimeter, but we thin them down to 100 micron or 150 micron. So that's important. We did some simulations. So the strain near the edges of the sample is of course non-uniform, you know, as it goes down when you glue it. But if you look in the middle of the sample, it's reasonably flat and uniform. And it is what you would expect. In fact, in the very first experiments, what I did is I put the strain gauge at the bottom of the piezo to measure the strain that the piezo produces, and the strain gauge on top of the sample, and compare them. And at low temperature, if you do the gluing right, they agree. I've gone to my reserves. You see in the new box. So that's good. All right. Oh. Later.
Okay, let's thank the speaker
Okay,
again.
sure. Thank you.